Vectors, an introduction for two-dimensional vectors in rectangular coordinate systems. Our objectives in these videos is to introduce the concept of a vector, to demonstrate geometric properties of vectors, to describe algebraic properties of vectors, and to connect the geometric and algebraic demonstrations concerning vectors. Some prerequisite materials include basic arithmetic, the rectangular coordinate system, working with angles, trigonometry, and inverse trigonometry. We begin with vocabulary in this video. A scalar quantity is a quantity that is completely characterized by a single real number. Examples of scalar quantities would be length, area, volume, or speed. The real number in a scalar quantity is termed a scalar. And as another example, suppose a person is 6 feet tall. This is a scalar quantity because it is completely characterized by a single value, and the scalar in this quantity is 6. A directed line segment is a line segment that also has a direction assigned to it. This is also called a vector. Examples of vectors would be velocity, acceleration, or force. Each of these quantities are incomplete without both a magnitude and a direction assigned to them. The initial point denotes where the vector begins, and in our diagram to the right, point C is the initial point in this example. The terminal point denotes where the vector ends. And of course, in the diagram to the right, the terminal point is denoted by A. Notice that the arrow in this directed line segment actually has its end at the point A. In other words, the line segment does not go through the point A. If it did, that would imply a ray, not a vector. A ray is basically a line that actually has a finite initial point but has an infinite end, and it takes 2 points to generate a ray. So when you're drawing these vectors, the arrow that's denoting this directed line segment actually points right to the terminal point in your drawing. So you don't draw it through, you draw it right at that point. The magnitude of the vector is the length of the line segment beginning at the initial point and ending at the terminal point. And in our example here, it would be the line segment CA. And this is often denoted with vertical bars surrounding the name of the vector or 2 vertical bars surrounding the name of the vector. So in this case, you can find the magnitude there is a formula. Basically, you take the sums of the squares of the components and take the square root of that. And this will be demonstrated in another video. Some additional notes here. Vectors are usually represented in boldface when typesetting and are usually lowercase letters. So here we can see the vector V, a boldface lowercase letter. But when instructors are writing on boards, vectors are still usually represented with lowercase letters, but they have an arrow drawn over them. Now, if you remember from geometry, it takes 2 uppercase letters, usually denoting the 2 points, that the ray would actually go through. And you'd have that arrow over that, beginning at the initial point of the ray and going through that other point denoting the ray. But when it comes to vectors, you only need 1 letter to denote the vector. So you have 1 letter, it's usually lowercase and not uppercase, and there's a little arrow over that when you're writing these things on the board. So when you're in a classroom and you see instructors writing a V with an arrow over it or a W with an arrow over it, that is denoting a vector. They just can't do boldface typesetting when they're on the board. It just isn't very feasible to try that. Now, another thing to really be aware of is that a vector is determined only by its magnitude and direction, but not its location. Vectors are not fixated at a location, so you can move them wherever you want in the coordinate system, as long as you maintain their direction and their magnitude. This implies that an origin of a coordinate system may be placed anywhere it is convenient to perform calculations. So this does give us a little bit of an advantage when it comes to arithmetic. So here's an arbitrary vector in two-dimensional space. Here we have a point C, we have a point A. C is the initial point, A is the terminal point, and there's no coordinate system associated with it. So we could have this vector placed anywhere we want. But once you put a vector inside a coordinate system, then its initial point and its terminal point will have ordered pairs associated with them. And in this example here, the initial point is located at the origin and the terminal point is located at 1, 3, implying a 1-unit movement horizontally and a 3-unit movement in the positive vertical direction. With a coordinate system in place, calculations can be performed to determine magnitudes and directions. So there are advantages to having a coordinate system in place. But since a coordinate system is not needed to describe a vector, the vector may be translated from one location to the other, provided neither the magnitude nor the direction are changed. So if you're going to move a vector from one location to another to do calculations, just make sure that when you move it, you're not spinning it around or stretching it out or shrinking it down. You simply pick it up as is and move it to the location you need to move it. So here's a vector with an initial point at the origin. Again, it's our same vector, 0, 0 to 1, 3. But here is that exact same vector moved to the point 1, 1 as its initial and the point 2, 4 as its terminal. If you notice, the direction of the vector has not been changed, and the magnitude has not been changed either. I still move 1 unit to the right horizontally. I still move 3 units up vertically. So this vector and this vector are exactly the same. It's just that one has been moved to begin at the point 1, 1 instead of the point 0, 0. And this brings us to the displacement. And the displacement represents the path of a point as it moves along the vector. So again, when you have ordered pairs, you're moving in a straight line from that initial point to that terminal point, and that is representing the displacement because that's the path that a point can take as it moves along that vector. The components of a vector represent the movement in the directions in order to completely describe this displacement. So you have an I component and a J component when you're talking about rectangular coordinate systems. And in these next two, or this next example here, we have two different denotions of vectors. We have the bracket notation, which has bracket A, B bracket, or you have the IJ representation where you have A times I plus B times J. And I represents the horizontal movement, and it's known as the unit vector in the I direction. And J is the J component, and that represents unit movement in the J direction. So there's a lot of language going on here. When you have an I component, you are moving horizontally. When you have a J component, you're moving vertically. The number multiplying I tells you how many units you move horizontally. So if A is positive, you move to the right. If A is negative, you move to the left. Same thing with B. If B is positive, then you move that many units vertically upward. If B is negative, you move that many units vertically downward. And that will give you the location of a terminal point, provided that the initial point is at the origin. And that brings us to the position vector. The position vector is a vector whose initial point is located at the origin of the coordinate system. The terminal point is located at some arbitrary point AB. So again, once you have a coordinate system in place, you can move your vector so its initial point is at the origin, or you can have the origin of your coordinate system placed right at the initial point of your vector, and that automatically makes it a position vector. The resultant vector is a vector that results from adding two vectors together or from multiplying a vector by a scalar quantity. And if we consider the rectangular coordinate system, the direction angle is the positive angle formed between the positive x-axis and the position vector. So here again, we're going to be starting from the horizontal, and we're going to be moving in a counterclockwise direction around a circle until we get to our position vector. Once we get there, that angle measurement is going to be the direction angle. So an example on the right has displacement measuring start from point C to point A from 0, 0 to 1, 3. So writing this vector's components would be 1 minus 0, the difference in the first components, and then 3 minus 0, the difference in the second components. But order matters in this case because you always, when you are finding the displacement, you always start at the terminal point and you minus the initial point. So you always take the terminal, the I component of the terminal point minus the I component of the initial location, the J component of the terminal point minus the J component of the initial point. And because the initial point is at the origin, this would be termed a position vector. Here we have another vector, just a different vector here. And this again represents from point C to point A, 2, 2 to 4, 8. And writing this vector's components would be 4 minus 2. That would be the I components of the terminal minus the initial. And then you have the J component of the terminal minus the J component of the initial, in this case 8 minus 2. And now you have this vector's components is 2, 6. So you move 2, so from any starting point, you move 2 units horizontally, you move 6 units vertically, both in the positive directions, and you end up at the terminal point, and that gives you a description of this vector. So again, the 2 and the 6 are not ordered pairs. This basically tells you whatever your initial point is, you move 2 to the right, you move 6 up, and that's where your terminal point is going to be for this vector. But this is not a position vector because the initial point is not at the origin. Now the direction angle, here we have a diagram. We measure from the horizontal counterclockwise until we get to our vector here. The initial point is labeled in yellow. The terminal point is down here in yellow. The vector u is here. And in this case, the direction angle is 225 degrees. Now remember, we always have a positive direction angle. We always measure from the horizontal in the counterclockwise direction. So in this example here, starting at the horizontal, moving in the counterclockwise direction until we get to that u vector here, will give us the direction angle. In this case, it's 225 degrees. Here we have an important theorem. Suppose that V is a vector with initial point P1 equal x1, y1 and terminal point P2 equal x2, y2. If V is the vector formed from P1 to P2, then V is equal to the position vector where x2 minus x1 is the I component, y2 minus y1 is the J component. So what this diagram shows down here is that if I take an arbitrary starting location, P1, and I have a terminal location, P2, the I component is going to be the difference between x2 and x1, those x coordinates for those points. The J component is going to be the difference between y2 and y1, and that's going to give the description of the vector. Now, I can always move this blue vector V so that its initial point corresponds to the origin because vectors are not dependent on location. So A and B, when the vector has its initial point at the origin, those values are the same as x2 minus x1, that's the same as A, y2 minus y1, that's the same as B. So because vectors are not dependent on location, they're only dependent upon magnitude and direction, we can move the vector from any arbitrary point in space to its initial point corresponding to the origin of the coordinate system. On this slide, we talk about the different ways of describing vectors. So we can use boldface letters, and we can use bracket notation where v1 and v2 are real numbers. And these denote the components of the vector. You can also write a vector in the ij format where you have a number multiplying I and you have another number multiplying j. So v1, v2 actually corresponds to an ordered pair in the rectangular coordinate system. And these numbers that form the ordered pair are multiplying the horizontal and vertical components of the vector because, again, we can translate the vector back to being a position vector. Now, you can also write it in terms of square brackets, like as a column matrix, if you will, where the first number, v1, will be the I component, and v2, the second number in the column, will be the j component. And you can always do this so long as v is a position vector, where its initial point is at the origin. A third way of describing vectors is using the magnitude times the cosine of theta I plus sine theta j. Theta is the direction angle between the vector v and I, the horizontal component. And again, this goes back to the definition of direction angle. Remember, the direction angle is always measured from the positive horizontal, and you swing out counterclockwise, just like we've always done around the unit circle to measure angle measurements. So don't forget that you're always multiplying this cosine theta I plus sine theta j by the magnitude of the vector itself. And that, again, that's denoted with the double bars here. This concludes our video on the vocabulary concerning vectors. In our next video, we will discuss the geometry of vectors. In this brief demonstration of the triangle law, we have two vectors, u and v, where they share an initial point. And what we're going to do is we are going to move the u vector so that its initial point corresponds to the terminal point of v. And this is known as the tip-to-tail method. And this lays the foundation for the triangle law. So we're going to go ahead and move this vector u. Notice that its magnitude and direction do not change, only its location changes. So we're moving it from one location to the other, and now I have two sides of a triangle, and when I put in the w vector here in red, this completes the formation of the triangle. And this is essentially what the triangle law for adding vectors is referring to, that if I start with the initial position of v and this terminal position of u, after I do the tip to tail, the tip of u to the tail of v, or some people interpret it as the tail of v to the tip of u. It's really just kind of depending upon who's explaining this. But once those are joined, then you can complete the formation of a triangle and have a vector w correspond to the sum of the v vector and the u vector put together.